Oh, yeah. So, yes, we are skipping. Sorry, we are skipping the end of part 3 right now.
Okay.
We're skipping the end of part 3, going to part 4. Because I was thinking to myself, I'm so proud that this semester I'm just kind of sticking with my order. And I'm like, wait a minute, no, I need to skip Clausius Clapeyron and come back to it. That's okay. So part 4, solubility. So solubility is actually talking about making a mixture, taking two things and seeing if they like to stick together. So here is our list of, what are there, 6 things, 1 through 6, okay? And 1 is the strongest, and 6 is the weakest type of intermolecular bond. The asterisks actually are where, for sure, you must have a mixture. Because if you have intermolecular bonds, and if you have an ion dipole, then that means you have an ion and you have something that's polar. Okay, if you have actually intermolecular bonds and you have a dipole, induced dipole, then you must have something that's polar and something that's nonpolar being stuck together. It's not to say that you can't have a mixture of hydrogen bonding. Yes, you can. It's just that chemical A and chemical B both have sites for hydrogen bonding. Okay? So note that that ion dipole forces are only possible in a mixture. 2 or more substances physically combined, and then that, as is the case with dipole, induced dipole. And then, like I said, it's not to say that the other 4 forces aren't in a mixture, because they still can be. But they can also be pure substances. And up to now, we've been just been talking about pure substances. Okay. So ion dipole forces. Okay, so basically we talked about ionic compounds where they break apart into cations and anions. And they are going to be surrounded by molecules, polar molecules. So ion dipole forces. And it looks something like this. Oops. So water is a pretty good solvent. So of course when we dissolve something in water, we've got a mixture. And this is, you could pretend that this is sodium chloride, crystalline lattice structure. So I think it's kind of fun how, of course, is water polar or nonpolar? Polar. Water is very polar, yes. And so what happens is those, the hydrogens, of course, carry the partially positive parts, and the partially positive bits then surround your negative cation, and the oxygen atoms carry the partially negative, and they surround your cations. So that works. So this is how, like, sodium chloride would dissolve. Okay, so dipole is associated with polar compounds, and induced dipole is associated with nonpolar compounds. That's why if you have intermolecular bonds that are dipole, induced dipole, you must have something polar and something nonpolar. And to me, I can almost, the whole induction of a pole or the induction of a dipole on something nonpolar, it kind of hurts my brain. But I'm like, well, if there's already a polar molecule, it's easier to induce a dipole, I think. But maybe that's just me. So here's a video. I hot linked this together last night. Let's see if it works.
The electron cloud of an O2 molecule is distributed symmetrically across the molecule.
Nonpolar?
The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
Makes sense. Okay. We're actually going to, of course, O2 is a gas at normal atmospheric temperatures and pressures, and we're going to talk about how, of course, can you get O2 dissolved in water? Yeah, you can. We're going to talk about the degree to which that happens. And this one. All right. So, dipole-induced dipole. Here we have, remember the carbon disulfide? Is that polar or non-polar?
Is that polar?
It's non-polar. It's the one with the yellow. It's the one we were just talking about, yeah? Basically, you have carbon in the middle, 2 sulfurs, and it's linear. And so the centers of negatives and positives coincide. So that's non-polar, and we're going to dissolve it in acetone. And acetone, by the way, you see these two CH3, we have a CH3, carbon, and a double bond oxygen. So it's symmetrical too, but it is definitely polar. So there is your acetone, and here is your carbon disulfide. And I guess it's just showing you to induce a dipole on the one end of the carbon disulfide. I guess that was kind of counter, it was, anyway. So if you've ever heard the term like dissolves like, that's probably what they're talking about is polarity. So polar things dissolve polar things, non-polar things dissolve non-polar things, and we're going to talk about that. In order for something to dissolve something, you've got to be forming those intermolecular bonds of the mixture. So polar substances will typically dissolve other polar substances. Non-polar substances will typically dissolve other non-polar substances. When I get to this part of the lecture, I sometimes, and I don't do a lot of like fixing up furniture and that sort of thing, but you can get varnish remover, okay, or even like fingernail polish remover. What you're doing is you're counting on basically the solvent that you're using to interact with the thing to dissolve it. So, yeah.
Most detergents for laundry are made with grease to get grease out.
Detergents are good at, actually, they have a polar end and a non-polar end. So they are smart little things. So if you've ever heard oil and water, do oil and water don't mix? Oil and water don't mix, right? And because water's very polar, oil is very non-polar. That's it, in a nutshell. But I kind of want to talk about the dissolving process. So assuming what you're trying to dissolve is polar, water's a great choice. Sometimes called the universal solvent, but I have to take exception to that because if it's very polar, then it's not going to dissolve nonpolar things. So there's a lot of nonpolar things out there like oil or grease that you might want to dissolve. So how universal is that? I'm just saying.
Are most things polar or non-polar?
Most, it depends. You figure, I'm kind of pointing at the periodic table. Hydrocarbons, carbon, anything containing just carbon and hydrogen, nonpolar.
Really? Those
Yeah.
are super common, right?
What's that? Yeah, they're relatively common. Yeah. But if you throw a little bit of oxygen in there, depending upon how much of the carbon chain you have, then you have a little bit of polarity. Yeah. So this is exactly what Mike was asking about. So organic substance, if somebody says, I have an organic substance, all they have is something that has carbon, hydrogen for sure, maybe oxygen, maybe nitrogen, phosphorus, kind of those nonmetals over there. So many of those are nonpolar. So here's one for you, and again, give me numbers any day. This kind of subtle sort of thing kind of drives me nuts sometimes. But if somebody says it's a molecule but it's only weakly polar, then go ahead and say it's weakly polar, so I'm going to basically kind of lump it with being non-polar. Okay? So weakly polar, kind of go non-polar. Because that's a subtle thing, I think. Direct those subtle things. Now this is kind of neat, okay? Remember when we talked about Hess's law? Basically, if you have a process from A to B, and say you can break it up into smaller processes like A1, A2, A3, A4, A5, A6, A7, A8, okay, and then get to B, okay, you can actually sum all of those processes together to understand the overall whatever's happening. As long as it's a state function. Remember state function versus path function? A state is independent of path. I don't care. Okay? So state function, independent of path. So we can look at this dissolving process like this, okay? Of course, our delta H's are enthalpy, that's energy associated with, okay? And here we're actually increasing enthalpy. This actually would be an endothermic process, okay? We have to separate the solvent molecules. Sometimes your two things you're mixing are in equal quantities, but solvent is there in greater amount. That's the difference between solvent and solute we're going to see here in a minute. So we have to separate the solvent molecules, break those intermolecular bonds. Endothermic? Yeah. And then we also need to take our solute, which we're trying to dissolve, and we need to break those intermolecular bonds. Endothermic? Yeah. So we have these two delta H's, okay? And then, so when bonds are broken, that requires energy. And when bonds are formed, what happens to energy? Energy is released, exactly. So then on the other side of the mountain, we get to see them combine. So once you break your solvent, break your solute, we're going to go ahead and make intermolecular bonds between the solvent and the solute. We actually have three different scenarios. When those new intermolecular bonds form, here's our first scenario. When the new intermolecular bonds form between the solvent and the solute, we could actually, with regard to an energy diagram, have less energy, okay? That means we had to put in this much energy, it gave up this much energy, it was a net loss. That's an endothermic process, okay? And our delta H's are what? Positive, okay? It could be that the third scenario is coming. Okay, so down here, okay, check this out, okay? We start here, add energy, we end up here. Net wash. Delta H, 0. I think we're going to call that a perfect solution, I think, in a minute. Okay. Alternatively, the last scenario is this one, okay? Put energy in, we have energy out. Okay, we have a net gain of energy. That would be an exothermic process, a negative overall delta H. Okay. And we're going to talk about favorable processes, spontaneous processes, and one of the things about something just automatically happening is if you release energy, that actually favors spontaneity. So it's going to be like that. Okay, so those are our three different scenarios. Energy in, energy out. How much energy out? Well, it depends. I just think that's so cool. Ideal. I couldn't think of the perfect, though I used perfect, but ideal. So an ideal solution is basically the energy required to break your intermolecular bonds of your solvent and your solute is equal to that released when those new intermolecular bonds form. And like this says, you basically figure, for instance, if you have two polar substances, you know, you break your dipole, break your dipole, you form dipole. Okay, might be about the same, okay? And what this says is you can predict the properties of the ideal solution from its components. The opposite of and we say this obeys Raoult's law. Now, is it Raoult's law that I skipped the end of part 3? I think so. We're going to come, no, that wasn't Raoult's. That was Clausius Clapeyron's law. Okay. So many different fun things. So Raoult's law. We'll talk more about Raoult's law later. I like Raoult's law. So a non-ideal solution would be kind of like we looked at with the diagram. Either it's an endothermic, energy is required, because you're not releasing as much as you require to break those intermolecular bonds, or it's a net release of energy, exothermic. Oops, sorry. I have 2 of those, don't I? So let's see. Most often with your enthalpy solution is negative. When the forces of attraction, that makes sense. When the new intermolecular bonds formed are favored versus the ones that are broken. It's going to be exothermic. This one is the new bonds that are formed are less favored than the ones that were broken. Endothermic. positive heat of solution. Okay. Oh, one more line. Are you serious? Do you have anything to fill in here? Okay. Right. Okay, so let's look at some figures. All right. So the black is carbon, the green are chlorines, and the white is hydrogen. Looks like a tetrahedral sort of shape. Seems reasonable that the centers of negatives and positives do not coincide. That's making this polar. Okay, here's our other one. Remember I said that, of course, the blacks are carbon, the whites are hydrogen. What's the red?
Oxygen.
Oxygen, yeah. Anytime you introduce oxygen into an otherwise hydrocarbon, think you can get a region of negativeness. Yeah.
Okay.
So that dot, dot, dot is a dipole intermolecular bond between those two. It's for this mixture. That's kind of showing you the partial region of positiveness with, is it like, yeah, with the hydrogen. It looks weird, but anyway. Okay. So generally speaking, we have these two terms, and they have to focus: immiscible and miscible. Okay, immiscible means they don't mix, and miscible means they do mix. Sorry about the similar terms. Immiscible means they don't mix. So we would say that oil and water are immiscible. Example, oil and water. And the reason they don't mix is because one is nonpolar and one is polar. And this makes sense. When are they not going to mix? Well, they're not going to mix when basically the attraction to form the mixture is weaker than the attraction to keep the substances pure. And it's been described that although oil, those nonpolar molecules, they're willing to do whatever. Those water molecules really like to hydrogen bond with each other. Okay? So they kind of exclude the oil in that way. So we have immiscible and miscible. Miscible then is where they do dissolve. Okay? They will go ahead and form a homogeneous mixture. And this may or not be kind of the equal, like the energy required to break the intermolecular bonds of the solvent and the solute, equal to the amount of energy released when those new intermolecular bonds are formed within the mixture. Remember, that's the ideal solution.
This might be off topic, but does this count just without heat? Like when you add heat, something.
Oh, I see what you're saying. That's true. That's
Okay.
a good point. Heat, you figure heat is good at being able to break intermolecular bonds. Mm-hmm. So with heat, your miscibility would increase. Okay. Miscibility, not immiscibility. They're so similar. Okay, so like dissolves like. Dun, dun, dun. I'm sure there's a song there for that.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
And I don't know where it fits in. This is kind of maybe one of the things Rhonda said. If you were to take this water and isolate it away from the oil and go check it, did you have any solubility of oil at all? Yeah, there's a possibility that you have just a small amount, but it's not the obvious amount. Okay? And heat would change that. Dr. Snipes, my husband, when he teaches this, sometimes he'll say water molecules are like the cool kids, which I was never a cool kid. The cool kids are like, oh, they're all clingy. And it's not that I think these guys are cooler, but Not that the nerds wouldn't like to mingle, it's just the cool kids are all like,
Won't let him in.
yeah, won't let them in. Okay, so here's a still image of, you can kind of see down at the bottom, ethylene glycol. So I'm hoping you see, what do you think about that OH? We'll talk more about how do you unpack the structure, but what's special about that OH in ethylene glycol? Hydrogen bond, exactly. Now, one of the things I didn't mention, and we've already run into it in a homework problem, is if you have two regions of OHs, guess what? You get twice your buck for your bang, okay? So the more, what we say, hydroxyl groups, then it can hydrogen jump on even more. So yeah, that makes that polar. So you think they should dissolve? I hope so, right? Your radiator hopes so. And this is kind of clever. You see the gray are the carbons, not black, but gray, and the white are the hydrogens, and of course the red are the oxygens. All right, now we have carbon tetrachloride is the solvent, the white part, okay? So carbon tetrachloride was that carbon in the middle and those 4 chlorines coming out. It was a tetrahedral molecular shape, and the regions of negativeness and positiveness coincided. So carbon tetrachloride, non-polar, even though it has polar bonds. And I said, what do you think about motor oil? Hydrocarbon. Also non-polar. Yep. Motor oil. So they're both non-polar, so that's why carbon tetrachloride will dissolve in, or will dissolve motor oil. Now this says, oh, but what are these molecules? They're water. Does the water dissolve the hydrocarbon? No, we're back to oil and water, basically. Where's my carbon tetrachloride? Oh, I guess it's... Okay. Do you guys recognize the water? I'm sure you do. And you recognize this yellow and white is your crystal lattice structures. Remember how that works is that the nonmetals pick up an electron or two, and that's what makes them bigger. And so they are negatively charged anions, and the white is a positively charged cations. So this is kind of what we looked at before. This is like the step process. So you need to break the intermolecular bonds of the water molecules. You need to break the intermolecular bonds of the crystal lattice structure, okay? And then red there is you need to form those new intermolecular bonds between the water molecules and the ions. All right. Polarizability. I feel like we talked about polarizability before, okay? Yeah, so if polarizability enters into the picture when you're trying to induce a dipole on something that's nonpolar. And we talked about this, that basically the greater the molar mass, okay, and that's where our sulfurs came in a little bit ago. The greater the molar mass, the more polarizable it is. And if it's polarizable, then you can get those induced bipolar, induced dipole, otherwise called dispersion forces setting in. So here we have this could be, well it is, an oxygen molecule. There's an O2 and there's H2O. I think we saw this with, a minute ago with, maybe it was O2 or I2. So what can happen is that water molecule can induce a dipole temporarily on an oxygen molecule. Yeah, we did see that, didn't we? Making this partially positive, then you can get that intermolecular bond, which this would be what? A dipole-induced dipole intermolecular bond. But how polarizable is that oxygen molecule? Well, we can kind of look at its polarizability of oxygen relative to some other gases. So, of course, nitrogen is a gas, hydrogen is a gas. As we go from oxygen to nitrogen to hydrogen, we're actually decreasing molecular weight. And then according to our thing, if we decrease molecular weight, what happens to polarizability? Does it go up or down? Decrease. Yes, it goes down. Decrease molecular weight, it's less polarizable. So what do you think? If it's less polarizable, is it gonna be, if hydrogen is less polarizable than oxygen, would hydrogen be more soluble or less soluble than oxygen? Than an O2 molecule? It's less polarizable.
Less soluble.
Exactly. Would be less. And that's what we got here. They're all not like really high, but units of these are how much, what mass in grams of that particular gas could you get to dissolve in 100 grams of water. Now, notice that, there's an asterisk there, this is at a temperature of 20 degrees. Temperature, very temperature dependent, because we're going to be talking more about that solubility of a gas.
So there's no like a term for solubility,
There's no what?
like degrees Celsius or an atmosphere, like a term like that?
That's a good point. If somebody tries to describe, puts a number with the solubility, they'll always have to give you units. There's no, yeah, because there's definitely different ways to describe solubility. In this case, it's just grams of the gas per 100 grams of water at that temperature. Yeah. Good point. Okay, kind of finishing up here. So this is actually, there's three substances here. We have a before it's mixed, and then after it's mixed. This is before it's mixed. Where we're dealing with that carbon tetrachloride, remember the carbon with the 4 chlorines where the centers of negatives and positives coincide. This is where we're talking about it trying to dissolve oil. It would dissolve oil, carbon tetrachloride. Nonpolar, carbon tetrachloride, oil, nonpolar. So notice then in the fraction above it, we've got two things. We've got water, which is polar, and we've got an I2 molecule, which is just I and I, okay? And that is nonpolar.
Where's that supposed to be in there? Are they mixed together right now?
Yeah, they're mixed together. And then they're mixed together, but then the way this figure works is you go ahead and shake the test tube. I think this is kind of fun. So what they're saying is to a certain degree, you can get I2 to dissolve in water, even though I2 is nonpolar and water is polar to a certain degree. But you can't get it to dissolve in carbon tetrachloride. You mix the two, and what you figure is that I2, which is nonpolar, is going to favor the carbon tetrachloride, and that's exactly what you see here. That's why it turned purple.
That's fun.
Yeah, I think so too. You give it a choice, and it's going to go where it feels most comfortable. Or those water molecules are going to shove it out.
Get out of here.
Yep. So then the next few slides just kind of talk you through what those look like. So here's the video.
Solid iodine is not very soluble in water. If the dense, nonpolar solvent carbon tetrachloride is added to the mixture, it forms a layer underneath the water. The nonpolar iodine is extracted from the water and readily dissolves in the carbon tetrachloride. The difference in color between the two solvents indicates that the iodine molecules interact somewhat differently with the solvents.
So in this one is a little different than the still one we saw because they don't show the clear water. But that was kind of neat. The carbon tetrachloride is more dense than water, and they kind of did that. Okay. Actually, one of the things you may have heard about is this. We're going to talk more about supercritical fluids. And all supercritical fluid is it's basically taking what is usually a gas and basically pressurizing it and finding that a temperature at which it forms it's like a gas, but it's like a liquid. It's like a gas, but it's like a liquid. It's different than pressurized like liquid nitrogen, supercritical fluid. I mention that because like carbon dioxide is a great supercritical fluid, and they can use that. This is my coffee bean. Actually, they can use that to kind of permeate the coffee beans and to extract the caffeine. So I need that caffeine gone. So it's science. Okay, so yeah, the next few I think just kind of show you. Yep, we have polar, nonpolar, nonpolar. Okay, structure, nonpolar, polar, nonpolar. Okay. And then on to this assignment. Take a quick look. One. So in this one, which of the following do you expect to be most soluble? So you only pick one of these, okay? And so I went ahead and make sure we're all on the same page, I wrote out what they are. Actually, this might be in your book even, I don't know. So we're trying to dissolve it in water, water's polar, so you're looking for something that's polar.
Something that's really polar.
Yeah.
Something that would be more polar than the others.
Right. And so for calcium carbonate, you may or may not know that that's actually chalk. And picture trying to dissolve chalk in water, no. And then I want to actually put a link out on our course Twitter feed because I was like, yeah, but not all salts, some salts dissolve in water. You know, sodium chloride dissolves in water. Why doesn't calcium carbonate dissolve in water? And I guess to me, it kind of, what the article I pushed out there says, it goes back to one of the things we're talking about. Like, you have to break those, you have to break this in order to dissolve it. And one of the things we know about the 6 intermolecular bonds, what's at the top? Ion, yep. That's what we have here. But then I was like, well, how come sodium chloride, you just break sodium chloride, dissolve salt in water? Well, again, it goes back to the energy to break it. So anyway.
I might be slipping a cog, but what is the NH2OH?
It's some sort of a mean.
Oh, okay.
Yeah. So NH2OH looks like this. So nitrogen. So what do you think? Is this polar? And how many people think this is polar? Yep, I think it's polar too. We definitely have hydrogen bonding here, here, and actually here.
Like really polar.
Hydrogen all over the place.
So, they're all hydrogen bonds.
Mm-hmm. Yeah.
We just gotta figure out which one is the most polary of the hydrogen bonds.
Well, you just have to narrow it down to the compound, so. This is a similar question. Which of these would be moderately soluble in something that's polar and nonpolar?
Ooh.
I know, I like it. And it kind of goes back to our idea of detergent. Detergents do that. They got 2 minds. They're like a polar end and a nonpolar end. Okay, so I kind of drew these out, make sure we're all on the same page. You guys might not know what 1-butanol is, but the all gives it away as an alcohol. The but part gives it away as having 4 carbons. We'll talk more about that. So there's your 1-butanol. This one is the naphthalene. We got naphthalene, like 2 benzene rings. It's kind of fun. Okay, bunch of carbon, bunch of hydrogen for naphthalene. For C, we have hexane. Okay, I went ahead and I just did normal hexane with all those carbons in a straight line. And of course, what are the oranges here? Hydrogens, yep. And then we have salt. So
you basically would want to find something that is pretty close in the middle of polar and non-polar.
mm-hmm. Yep. And like I said, give me numbers any day. Sometimes I'd be like, give me numbers.
Yeah,
You know,
If you
I
don't
know.
ask and it's off topic, but a big thing in geology is that what they call karst topography, and basically like in Florida and stuff, they've got these massive sinkholes, and it's because when water runs through the calcium carbonate, it forms an acid,
Okay.
carbonic acid.
Okay, yeah, that sounds right.
And I was gonna say, like, so the water does something to it, but it doesn't dilute it, or,
Interesting.
I'm not sure, I was wondering how that works out chemically, but maybe
I don't know, yeah, I'd have to look at it, but I'm sure it does.
it's whole from it.
This one goes similar. What are, let's see, substances, one of the following will dissolve in both polar and nonpolar. So looking for something that's polar and nonpolar. That's that
It's
one.
basically, it's exactly the same as 3.
Uh-huh. And here's this one.
two,
They're
I
all they're similar. And this one actually, the things I have there, they're already in the book. No problem. Look for varying degrees of polarity. 2 of these substances are highly, 2 are slightly, and 2 are insoluble in water. I hate these. This semester I'm just owning up to it. but you can do it, look for which is the,
There are
the ones
two that are
most
very
polar.
soluble in
Yeah,
water
the
and
ones
two
that
that
are
are
most polar.
not.
Most non-polar will be your two that are not soluble, most polar will be your soluble, and then the two you didn't pick would be your. Okay,
Boy, propylene glycol.
I know. That's true, a lot of OHs, you increase
That
those
is
OHs.
polar.
Yep. Okay.